So yeah, well, uh, welcome everyone to my presentation. Today I'm going to talk about Flexecutor. It's what we call out-of-the-box smart provisioning that's suited for serverless workflows. Today what will be presented instead of Enrique Molina because of the weather. So I will try to do my best in order to explain uh, our, our application. First, I'm going to introduce briefly our group. We are the Cloud and Distributed System Lab. We are a common contributor to middleware, and we are actively participating in four large-scale European projects right now, of which three we are coordinating. And in specific, I want to remark the Extract project, which is the one that we work with in order to make the tool that we will present today. Also, it is worth mentioning that in the group we have some strong relationships. We made some collaborations with IBM, with Dell, and some others. And we also focus not only on research, but also on producing production-grade solutions. As for example, Lithops, which is a well-known tool in the serverless computing paradigm, and also Dataplow that allows to do on-the-fly partitioning of datasets in order to parallelize data input in all these serverless workflows. Now we move on to the contest. We will first introduce the motivation for the serverless smart provisioning. Then we will comment about the state-of-the-art solutions that are present right now and their shortcomings. We will then explain how Executor fills some of the gaps that the current solutions are not addressing or are not concerned about. And then finally, we will review the design, the implementation of Flexecutor. We will present some evaluation and testing, and that will wrap up this presentation. Here, we can see a very simple diagram that also relates on how simple, in theory, the function as a service model is. We only theoretically need to provide our code, our input data, and nothing more. And with nothing more, the provider will execute transparently your function. We don't need to worry about underlying infrastructure. We also know that with most function as a service implementation, we have a very high scalability, and that you only pay for the resources that you use. All these features make it a very attractive model for the end user. Most of the times, this end user use FAS for things like HTTP requests, web servers, small security checks. But there is an alternate usage that we and the community believe that is rather interesting. That being the serverless parallel processing paradigm. This paradigm consists of a huge processing problems that we can manage to execute with function as a service, utilizing most of the time partition of data, both in vertical and horizontal ways, meaning that we can define, for example, directed acyclical graph or DAGs for this pipeline. But since function as a service by itself forbids direct communication between functions, we usually need a third-party broker to ensure communication is able to happen. Inside this, inside this, inside the serverless parallel processing, we can also find some features that make it a very attractive solution. Like provisioning is usually very fast. You pay, as we said before, only as you use the resources. You don't need to manage the backend. And there's also a lot of potential in a burst potential or burstiness, as we wrote it here, making it a viable competitor against cluster-centric technologies such as Dask, for example. In here, the problem, or rather the challenge that appears with serverless parallel processing, is that you need to select the right resources and configuration for your pipelines. Let's say, for example, I have this huge function with variable stages. I know I need some parallelism, but how many parallel functions shall I have? Shall I allocate more memory or less memory? I don't want to under-provision my function, should they fail, or over-provision them, should I be charged for resources that I'm not utilizing? Also, maybe I want to have the fastest execution regardless of the cost. Or maybe I just want the cheapest way or a trade-off between the two. That's usually the case where you want to find the most cost-effective ways to execute regarding time and cost. And that's where smart provisioning comes into play. There is many existing literature on the smart provisioning concerning on how to solve this problem. We have Jolteon, Kairos, Ditto, Orion, and they are really good words, exemplary solutions to smart provisionings, but they do have for some shortcomings. We find that for state-of-the-art tools, there are many variables that affect these solutions. As you may observe on this table, most of them are not open source. Therefore, we don't have direct access to the code, and this sometimes can make it harder for the end user to utilize this code. Even in the open source solutions, we still find problems. Are these tools bound to a cloud provider? Can these tools manage a DAG? Can it be used to orchestrate executions? Are we given an API to use? And just by looking at this table, we can see there is no solution that satisfies all or even most of these features. And that's why we found necessary to cover these limitations and to give the user the tool to cover all his needs regarding smart provisioning. This is the main motivation of Flexecutor. Flexecutor is a Python library with a simple API that can operate on multiple providers with the same lines of code. We also wanted to implement a simpler DAG orchestrator across different execution stages. And finally, but very importantly, we don't want the users to deal with the smart provisioning code. We want them to focus mainly on the orchestration and the actual implementation of the functions that need to be executed. Here we can see Here we can see a simple overall diagram where you can see the 5 main primary functions of Flexecutor that we will now explain. First, you have the profiling. In the profiling, you want to get different samples with multiple configurations. So we need to sample these results so our DAG can then proceed to the train stage. In the train stage, the model is fed with our sampling data, and here the model is able to learn from the resources configurations and their impact on the pipeline. A trained model then allows us to proceed to the prediction of configurations. With these predictions, we can now optimize the resource configuration of our pipeline, finally resulting in the execution step. Regardless of provider of the code, we can know perfectly no, but we can pretty accurately determine the best resources for our application. Here also, we can observe that we might as well specify our own configuration if we needed to have a specific type of configuration that's not determined by the profiling. Here, we can see a class diagram that mentioned previously. Our solution works over lithops. Lithops allows us to easily run over hundreds up to 1,000 functions with ease. So we found that it's the best tool for our application. And here we have also the definition of the DAG executor. This is the logic that the user is not seeing, and the scheduler. The scheduler takes one of the we have four, but there is no limit to how many you can introduce, and the user only needs to specify which one needs he wants to use and how he wants to optimize. For some of them, you can optimize board cost, some of them you can optimize both, etc. In this stage, the great part is where the user actually defines the stages with flex data, both for inputs and outputs is the same definition, and defines the logic of the DAG that we will see in the next graph. We can see that this only occupies about 5,000 lines of code. And then we can talk about how to actually make a Flexecutor app. We find that it's rather simple to define a function with Flexecutor, meaning that you only need to define the function itself. In this case, we have made a very simple word count, where you can see that you get the context. From the context, you get the path, input or output. With the input, you open the content by itself. You just do the count of the word count, and then you return it and write it in the output. And in the main orchestrator of the DAG, you can see how you only need to define the name, the stage. In our case, we have made a real stage, only the map stage of the word count, and we have not defined a real second stage, but it's just to show that it's possible to define as many stages as you need with the function, the input with the flex data, and the output. Then, in an Apache Airflow style, you define the order of execution of the stages that can be linked or they also can be independent. So you can have a mix of both. And then you just add those stages to the DAG and you perform the DAG executor. And if you want, you can do the profiling, the training, the optimizing, or just the simple execution. We also have already some apps that you can test in Flexecutor. You have the Titanic step app. That's one stage that makes a single tree of execution based on the node model, a video app based on the Pocket, a machine learning app based on Cybros, and the most interesting one for us is the astronomy app. That has 3 stages. It's a very data-intensive app, and it's a real application that was used in the Struct project. Meaning that this proves that we have some real applications for our software and that they have been used for these real workloads. Finally, we have a little bit of evaluation. First, in this part, we can see how much code is abstracted from the user by using Flexecutor, meaning that traditionally, if the user wanted to implement any of these, he will have to write at least this many lines of code corresponding to each implementation in order to have the functions as smart provisioning. Now the user can just boot up a Flexecutor function, and he doesn't need to care about any of the smart provision integration. And here we have done some testing to prove that there is no real difference or latency or degradation on using all these 4 state-of-the-art provisioners over by themselves or with Flexecutor. Then we have this table explains how many lines of codes you save even when using a single application, for example, the machine learning application or the Titanic application, over writing it with lithops versus writing it with Flexecutor. As you can see, you save amount of time, making it more accessible and transparent for the user. Finally, we can see that the orchestration time, respecting the total execution, is not really significant. So we are making sure that we're not adding overhead by using our application. Finally, to wrap up, it's important to say that the research in the serverless map provision is very broad. but we also believe that it's very extensible. We know that the hardest part of smart provisioning is actually the smart provisioning, but we felt the need to bring all these advancements in provisioning to the end user because as of today, it's really hard to program, for example, using some of the open source or even not the open source applications to implement, and they are bound to one provider, and maybe you want to work in other providers. So what we wanted to focus is on that, on solving the limitations, mainly in usability. So this is an application for the end user. We also have evaluated and it's ready to use. You have here the link to GitHub. You can also scan it. And to end, Enrique always likes to add, and I will add as well, a little call to action. To if you're planning on making a new smart provisioning, why not build it over Flexecutor? Since you can already test against the other ones, and then it will be available for everyone. So, thank you for your attendance. Thank you for everything. And now, if you have any questions, I will try to answer them. I will try to answer them as well as I can.
Thank you. Thank you, Octavio. Do we have any questions from audience? Okay, I have actually two. Go ahead, Andy.
No. Nobody showed up in the room.
Okay, so definitely no questions.
There is one
Okay.
question. There is one question.
No, there was one person. I don't know the question. I think it's clear.
So, you have a question?
I don't have a question.
Oh, no, sorry, no question.
Okay. I have actually two questions. So
Sure.
one, if you go to the previous slide, you emphasize how easy it is to use it.
Yes.
So how easy it is to debug it, or when something is not working, do you provide, like some debugging or observability, or what kind of tooling to watch executor, and then if something is not working, to fix it?
Well, there is some debugging capabilities, both included in the base of Lithos by itself. And since Lithos is always configurable by a file, you may change the config file in order to show further debugging. But I couldn't tell you right now if there is a more in-depth debugging feature provided. Yeah.
That's okay. And then the second question, so do you know if anybody like outside of your group is using Flexecutor today, and what kind of feedback they provided?
I personally, I don't know if anybody is using Flexecutor, but because since, as far as I'm aware, it has not been publicly available for that long.
Okay.
But I personally did, for example, when we talk about the astronomic application, I, without previous knowledge of Flexecutor, because I entered late to this work, I used it to create the astronomy app, and it was by following the examples that you find in the Titanic's app, the video apps, and all, it was pretty easy to follow along just with examples and implement another workflow.
Okay. Sounds good. So the future looks bright, right? That should be. Okay. Do we have any other questions? If not, we will move to the next presentation. Okay, so next presentation is actually by Erfan Darzi, but I think he may not be able to present. So I will just play back. He provided the backup recording. And maybe he will be able to join for questions in Discord. He was trying to also to call in into the our workshop, but I don't think he was able to. So let me just play it back, and then After that, we have one more presentation, and I see Yassine, you are already here, and I think you already tested your screen sharing. So let's start with the second presentation, which is Erfan talking about serverless and HPC using. Okay, a second, I will share my screen. Let me know if you, well, if you do not see the screen or anything is wrong, let me know, and I will start playback. If you cannot hear it, please stop me.
Good afternoon, everyone. Today I'll be presenting our work on an eBPF-based telemetry system for root cause analysis of GPU tail latency on cloud virtual machines. This is a work with my co-authors, Aldo, Srinanath, and Kaveh. We are presenting this at the workshop on serverless computing. In multi-tenant cloud environments, GPU workloads frequently encounter unpredictable tail latency spikes. These spikes are particularly problematic because the root causes are opaque to the users. And the causes of these spikes of latency could be quite diverse because of the different players that might actually contribute to these spikes. To name a few, NIC contention from network traffic, CPU scheduling issues, and I/O pressure, or PCI bus saturation could be contributing to the tail latency spikes. And the key challenge here is what we call the renter constraints. The users operate within a guest virtual machine with restricted privileges. They cannot see what's happening at the host level, and they certainly cannot access the hypervisor or inspect the other tenant's activity. That actually causes the main problem that for diagnosis and fixing the tail latency issue, this permission problem actually limits the tenants a lot in these scenarios. Traditional GPU-centric monitoring tools, for example, NVMO, are very good for GPU internal metrics, but they fail to capture these broader system dynamics. So, for example, when you see high GPU latency, you cannot use NVMO to tell you whether it's due to a networking issue or it actually comes from another root cause. So for that, we need to do a root cause analysis to correlate GPU events with host level metrics. So now we move on to the contributions of our work. So we mainly contribute in two different ways. The first part is that we propose a unified and host-only telemetry framework, and we use eBPF for that. This framework captures system-level signals across multiple layers that it actually captures network activity, CPU scheduling, and I/O operations. The key advantage is that it's lightweight with no intrusive instrumentation required. We are not modifying kernels or drivers. We are just attaching a standard eBPF probes to the existing trace points. Secondly, we built a correlation engine for root cause diagnosis so that we can actually analyze the trace points that we get from the eBPF for the first part, and then we transform and then we analyze them to process the telemetry data in real time so that we can identify the causes of the latency spikes. It uses lagged cross-correlation with spike scoring to identify temporal relationships between host-level events and GPU performance issues. So now we move on to the system architecture. Our telemetry collection operates at 3 distinct levels. All of them are synchronized to a single monotonic clock. First, we start at the kernel level, where we use eBPF probes, where we sample them at 100 hertz. For network monitoring, we track NetRx soft IRQs and NIC queue length. This gives us direct visibility into network bottlenecks that can delay GPU communication operations. For CPU contention, we trace switching events to identify preemption and the scheduler pressure that can starve the GPU driver of the CPU cycles. And for I/O, we track block I/O events to identify disk access patterns that might cause PCI contention. So basically, all of these metrics are coming from eBPF probes, and they give us deep insight into kernel level events that will be used together with the GPU metrics that I'm going to describe the process right now. And then altogether, they're going to be analyzed for diagnostic analysis. For GPU level metrics, we use NVML, and we collect the information at 10 Hertz. This includes the standard GPU telemetry like utilization, memory usage, power draw, and temperature. And also critically, we monitor PCIe counters. We track the data transfer rates between host and GPU, which is essential for identifying data transfer bottlenecks. At the application level, for distributed workloads, we intercept NCCL collective operation calls. This gives us fine-grained timestamps for different phases of operations, like all reduce, the setup phase, the communication phase, and the completion phase. So the key point here is that we actually innovate by the synchronization. So because we actually can gather all these signals like separately, but because we do them in an aligned way in a single monotonic clock, we can actually enable our analysis, which is actually based on the temporal correlation. And when we see a spike in the GPU latency, we can look back and see what was exactly happening in the host kernel at that moment. So the next question would be, how do we turn this raw telemetry into actionable diagnostic, which is our next slide. So this is actually our correlation engine, which operates on a sliding windows of telemetry data, typically 5 seconds worth of samples. For spike detection, we use 3 sigma threshold or 3 standard deviation on the GPU latency baseline. We compute the mean and threshold deviation and standard deviation of the threshold over a baseline window. And when a new observation exceeds 3 sigma from that baseline, we can declare a spike. And then the spike score is shown here is actually equals the maximum of the level of the signal minus the average over the sigma, which quantifies how extreme is the deviation over like the normal baseline. And once we detect a spike, the key step is to do a cross correlation with the host metrics. So we compute the correlation coefficient between GPU latency and the host metric at different time lags. And we use lags because we know that the host level events often precede the GPU effect by tens of milliseconds. So that's basically a cause and effect relationship, that there is some millisecond waiting time between them. For example, a CPU scheduling delay might affect 50 to 100 milliseconds before we observe the resulting increasing in GPU latency. So after we have these correlations, we need to find the potential causes. And for that, we use a weighted confidence score that combines top factors. So we actually use the spike score, which we get it from each of these metrics, how much it is deviated from the baseline, which we discussed it earlier. And we combine it with correlation coefficient and how temporally align it with GPU spike. So it needs to be both a strong spike. Also, it needs to be highly correlated for it to be considered as a high confidence signal. And then we weigh them. We weigh each of these components equally. So half of the contribution comes from each of them. And the system can diagnose 4 main categories: NIC contention from network traffic, PCI pressure from I/O, or DMA contention. Also CPU interference from scheduler issues, and GPU throttling from power or thermal units. So this approach is actually based on the causality testing. If one metric, for example, M, correlates strongly with GPU latency L at some lag, it's likely a contributing factor. So basically, this is a combination. And then, so this is actually our hypothesis that such a system could predict the root causes, and then we need to, of course, evaluate to see how does this work in practice, which is actually the next part of our work. So our evaluation ran on a single cloud virtual machine equipped with an NVIDIA A100 GPU. We had root privileges within the guest OS, which is what our system requires. For workloads, we used two scenarios. W1 is a synthetic NCCL benchmark. The all-reduced performance test with message sizing ranging from 1 kilobyte to 64 megabytes. This represents the communication primitives used in distributed learning. And the second workload is an optimal LLM serving workload using Triton inference server, representing a latency-sensitive production scenario. To simulate realistic multi-tenant interference, we injected 4 types of disturbances. D1 is I/O pressure, which we use FIO tool to generate high throughput disk I/O, which actually creates a PCI contention. The second disturbance is CPU contention. We pin CPU bound processes to the same cores that are being used by the GPU workload to create a scheduler pressure. The third one is NIC burst, which we use a TC utility to generate saturating network traffic. And the fourth disturbance is GPU throttling. We artificially lower the GPU's power cap to induce thermal throttling. And then the next question would be the result. So the next step is that we get the results. So here you can see the results. The accuracy actually ranges from 81% to 88% across disturbance types. For NIC bursts, we have 88% accuracy. For I/O pressure, we have 86. For CPU contention, we have 83. And for GPU throttling, we have 81. And for time to RC, we have 6 to 8 seconds, which is 3 to 5 times faster than manual analysis. So we see that the NIC bursts are detected with the highest accuracy. This is because the soft IRQ spikes have a very strong temporal correlation with GPU communication latency, and the correlation coefficients often exceeds 85%. And for I/O pressure, we have 86% accuracy, which means that when the disk I/O saturates PCI bandwidth, we see clear patterns in both clock I/O latencies and PCI block counters. And also CPU contention is slightly harder because scheduler effects can be more subtle and delayed. A brief preemption might not immediately manifest as a GPU spike. And GPU throttling is 81%, which is the most challenging because thermal effects develop gradually and power cap changes can be hard to distinguish from intentional clock adjustments. So the key points here is like we are achieving profiler grade diagnostic accuracy with monitoring grade overhead. And how does this compare to the other methodologies? So GPU-centric methodologies such as Elmongi et al., which actually does CPU to GPU synchronization diagnosis, which focuses primarily on GPU side metrics, they have very low overhead, but also the accuracy is around 62%. They cannot link host level events like NIC saturation to GPU stalls, so they missed most of the class layer causes. And also their RCA time is quite slow. So the cluster analysis approaches such as the one that is mentioned here, they use aggregate cluster metrics and they achieve 68% accuracy. However, they lack real-time per virtual machine diagnosis capabilities, and they still require a significant time to actually operate. The deep profiling systems such as eGPU, they have a better accuracy, but they do it through comprehensive kernel level tracing. But their overhead is also quite high compared to, for example, GPU-centric ones. These tools also sometimes require fabric-wide access, which is not available all the time in GPU environment, especially if you are only having guest-level access. Our system achieves 84% accuracy, And because our low overhead is relatively low, we have a better RCA time. So that means that we bridge the gap between lightweight monitoring and heavyweight profiling. The cost of the approach that we are proposing is actually monitoring grade, which is a sweet spot for production and deployments. And there are certain key insights from our evaluation, which we're gonna go over them in the next slide. So we draw three main insights from our evaluation. The first one is we could successfully bridge the accuracy overhead gap for years. There has been a trade-off, and you could have either lightweight monitoring or heavyweight profiling with better diagnostics. But by using eBPF for efficient kernel space collection and focusing on only correlation, we can actually use the most informative signal to achieve 84% diagnostic accuracy with very low overhead. And the key to our analysis has been the cross-layer correlation, which has been shown to be essential for accurate diagnosis. Single-layer approaches such as GPU-centric or network-centric, they achieve lower accuracy because they miss some important causal relationship across layers. For example, NIC-Q buildup affects GPU collective latency, but you never see that connection if you only look at GPU metrics. So the utility of eBPF is that it enables the unified host site visibility across all these layers without intrusive kernel modification or driver instrumentation. So the third insight here is practical deployment constraints matter in the real world, and many research tools assume access to network fabric telemetry, intrusive kernel hooks, or special hardware support, as we can see in deep profiling. In multi-tenant clouds, especially serverless environment, you often have none of this. Our guest VM design makes it actually deployable in such constrained environments. So as far as the limitations and future work goes, we first acknowledge that our work is actually a reactive system, which means that we only diagnose the spikes after they have been actually affecting our system and after the occurrence. We are able to detect and correlate the event, but the transient interference might have passed once we see the diagnostic signs. But also we need to know that our system is relatively fast, which we have like fast enough RCA time so that it will enable the operators to take mitigative actions before it results in a job failure or it cascades. So a logical follow-up would be that the future work can be actually exploring predictive models instead of reactive models. The second part is we have limited GPU internal visibility, which places our work unlike some other works that have white box approaches such as deep profiling or eGPU. But we need to acknowledge that this trade-off is deliberate. We want this model to be compatible with any guest virtual machine, and we are not aiming to be a deep introspection machine. So that means that some of the GPU internal issues will remain opaque to our system. The third part is that our correlation engine is rule-based rather than learned, which means that we have domain knowledge about how the interference manifests. But if there is a novel or more complicated pattern, we are not able to detect based on this mechanism. A good future work could actually use machine learning for anomaly detection and use complex pattern recognition to have a higher accuracy model, but that requires substantial label training data that's hard to obtain. The fourth part is we have some stable statistical baseline, which our model for spike detection relies on. In a highly dynamic multi-tenant environments, the workload characteristics shift frequently, and maintaining accurate baseline is challenging. We may need to do adaptive baseline estimation techniques. For example, we can do online change point detection to adapt to the changing baselines. So the next and the last part would be conclusion and summary. So as a wrap up, the summary of this work is that this is the first eBPF system for GPU tail latency, RCA in cloud virtual machines. It achieves very high accuracy with only 1.2% CPU overhead, and it enables fast diagnosis without fabric access or intrusive instrumentation, and it demonstrates practical viability for multi-tenant serverless environments, and it opens the path for renter-side observability in GPU cloud computing. Thank you very much for your attention.
Okay. So that was the playback of the talk. So we cannot really ask live questions. If you have any questions, ask them in Discord. And I think we should move to our last presentation, which is Yassine. Can you share your screen?
Yes,
There.
I hope you can see my screen.
I can see your screen. Everything looks great.
Okay, then let's begin. Well, first of all, hello and welcome to my presentation. I am Yassine. I'm joining you today from the Technical University of Berlin to present our paper entitled Sustainable Serverless Computing, a Taxonomy of Challenges and Solutions. Let's first begin with the motivation behind our work. Well, despite the green promises of big cloud providers and data center operators, the reality is still, unfortunately, gray. In 2018, the global computing industry accounted for an estimated 3.7% of the total greenhouse gas emissions, surpassing even the commercial aviation sector, which accounted for approximately 2.5%. And these numbers are even believed to have grown since then, especially with the emergence of AI and LLMs. And the real numbers that are not being reported are even believed to be much bigger because of the lack of transparency on the provider side and on the complexity and challenges faced when measuring and reporting such metrics. Well, serverless computing is a paradigm that came and promised a more efficient cloud. I'm not going to define serverless as we are in a serverless workshop, but in comparison to traditional cloud, where the user would provision a VM that would run for hours to only work a few minutes, with the serverless model or the function as a service model, you can invoke your code whenever you want it via HTTP requests or some kind of event that you set. So behind the reduced idle and wasted resources advantage and the pay-per-use savings hide many challenges, such as the code starts that are introduced whenever you invoke your function for the first time or after a long period of inactivity and due to virtualization overhead. In fact, a simple GET request in a fast system was proven to consume up to 15 times more energy than on a traditional HTTP web service. Other challenges specific to serverless computing also include the limited user control, the unpredictable performance, and the opaque deployment and scheduling within the serverless platform. So we wanted to delve deeper into these challenges and defined our research questions as follow. The first research question is, what sustainability-related challenges have been reported in serverless computing? The second one deals with the proposed solutions that address these challenges. And we didn't want to stop here. We wanted to categorize and organize the papers and the work that we gathered into a structured taxonomy. Now, to achieve our goal, we followed the systematic mapping study approach, which consists of three key steps. First of all, the retrieval of the papers. Second, the selection of the relevant ones. And third, the classification of the relevant work. In the first step, we defined the research questions as I introduced them. We used them to manually look for papers that are relevant to our topic. We call these the gold papers. And these papers allowed us to understand more the topic and gather some keywords that we use to define our search string. And the final search string looked like this. So the first part of it deals with serverless, because we wanted our study, or the studies that we find to be focused on serverless computing. So we find keywords like function as a service and all words derived from serverless. And the second part deals with sustainability. So we used keywords like carbon, green, and all words that can be derived from energy or sustainable. In the second phase, we took all papers or before we came to the second phase, we made the search in 4 major scientific databases, including IEEE, Explorer, and ACM Digital Library. And we ended up with approximately 5,000 papers. For the selection process, we defined inclusion criteria. So we included only peer-reviewed publications written in English that were published between 2013 and 2025. Because serverless got attention with the introduction of AWS Lambda around 2014, and to make sure that the studies we gather are up to date. And then we use some Python scripts and OpenAI models to exclude the duplicates and to check for relevance. And the papers that made it through this filter went through the manual selection again, and we ended up with 139 papers, which we reviewed again and used for the final taxonomy. Now, it is important here to mention that although we follow the systematic principles for systematic literature review, our study does not include formal quality assessment of the papers, and that's why it's just a systematic mapping study where we classify the gathered work into the taxonomy. Now, the final taxonomy looks like this. It is presented as a layered triangle. It has 2 main dimensions. You can see here on the left, we have the provider side and the user side. The provider side deals with the challenges and solutions related to the serverless provider or serverless platform provider. And on the user side, we deal with challenges and solutions that are related to the user or the developer. If we look at the taxonomy, we see that within the provider side, we have many layers. At the bottom, we have the policies that the users, that the provider, needs to consider and respect. Above it, we have the hardware, which is the infrastructure for running the functions. And above it, we have the software layer, which is basically the serverless platform that runs on the hardware. And then we have the deployment layer, which is the interface, let's say, between the user and the provider. It's the point where the user and the provider meet. So the users write their code, package it, configure it, and deploy it to the platform, and the provider receives it. And right at the top, we have the application layer, which represents the code that is entirely written by the user. In the following sections, we'll go through each layer, present the associated challenges and solutions that we found, or the relevant ones at least. So we begin with the provider side. So the provider holds the responsibility of building a sustainable foundation to run the functions, and beginning with the policies, specifically with the policies coming from external parties, so not from the industry. We call these the driving forces. So as an example, we have the European Union's 2023 revised energy efficiency directive, which sets energy efficiency first as a core legal principle for big companies. And it mandates the annual reporting of energy and carbon emission-related metrics. For instance, we have the power usage effectiveness, which was already presented in one of the previous presentations. But again, very briefly, the power usage effectiveness that the providers need to report is defined as the total available energy divided by the actual energy that is used by the IT equipment. Now, in an ideal world, of course, the PUE would be 1. if there is no leakage or waste of energy, but hyperscale or efficient data centers achieve numbers around 1.1 or 1.2. Another framework is the Corporate Sustainability Reporting Directive, which requires the disclosure of Scope 1, 2, and 3 emissions, so the direct and indirect emissions. There are also industry policies. One of them is the Climate Neutral Data Center Pact, started in 2021. This pact sets binding targets, and all parties and all providers or operators that sign this pact commit to meeting the sustainability metrics in all European Union data centers. And the current binding target is achieving 100% renewable energy by 2030 for the existing data centers. Major serverless providers such as Google, Microsoft, and AWS have signed this pact, and many of their data centers are also climate neutral. Now, moving to the hardware layer deals with the whole infrastructure on which the functions run. So the first challenge for the provider is choosing the right site or the right location for their data centers and for their servers. They need to choose it in a sustainable way if they want to tackle the sustainability issue. So in a location where the carbon intensity is low and the climate is cool, to reduce the energy used in the cooling system. For instance, Microsoft found in 2020 that data centers underwater are reliable because they can make use of the natural cooling. Now, other aspects include the server architecture, the processors that run the functions, and the memory. Regarding the processor, providers need to provide efficient architecture. Many studies emphasize that ARM-based servers are more energy efficient and provide similar or better performance, even some workloads, compared to the traditional x86 servers. We will come to this in a few moments again. And regarding memory, providers can also make use of dynamic voltage and frequency scaling techniques, which are implemented, for instance, in the memscale framework that adjusts the memory speed and power based on the workload of the user to reduce the energy consumption. Other aspects also related to the hardware is data locality. Of course, we can achieve reduction in energy consumption by co-locating compute and storage to reduce data movement. And the network connection is also a big part of the cloud paradigm. So optimizing the data transmission also lowers the energy consumption. For instance, using fiber instead of copper or wireless connection. Now, coming to the software layer, which is basically the serverless platform itself with all components like the autoscaler, the scheduler, etc. We begin with the scheduler. So one way to reduce the carbon footprint and the energy consumption is reducing the cold start overheads. And to do so, many providers are using lightweight virtualization and runtimes. For instance, AWS Lambda uses the micro VM monitor firecracker. WebAssembly is also a lightweight runtime. Again, one of the presentations of the previous presentations showed how the execution or the cold start is reduced through WebAssembly. Another approach is using pull-based schedulers, which or in which the scheduler doesn't distribute the work across the invokers, but it's the other way around. So we have the invokers that pull the tasks or the functions from an execution queue. And these algorithms, at least Hiku, a recent algorithm, achieved a reduction in response latency of up to 14 or 15% compared to the traditional push-based schedulers. Another scheduling approach is the spatial and temporal based scheduling. We know if we have a flexible workload, we can shift the execution in time or to a time where the carbon emission is low. Also, when we're talking about the spatial shifting, we can also shift it into a region where the carbon emission is low. And many middleware or many frameworks are used as middleware in serverless platforms, such as Caribou, Green Korea, and EcoLive. They all make use of the spatial and temporal based scheduling, and they achieve up to 66% of emission reductions. Although it is worth noting here that by shifting the workloads, the SLOs or the service level objectives can be violated. And this is where the intelligent allocation scaling come. So CASA framework, for instance, is an example of a framework that optimizes the scheduling to meet both the demand of the user and to lower the CO2 emissions. And it achieves up to 2.6 times lower emissions and 1.4 times reduction in the service level objective violation rate. Another major trend which we noticed when gathering the work is the use of AI models and LLMs for every kind of optimization, dynamically scaling resources, the smart placement of functions, etc. And although these can have their advantages, there are many considerations that need to be taken into account when using AI models, and we'll come to this again in a moment. The last aspect of the software realm here, which is also the most important challenge, in my opinion at least, is the lack of standardized measuring and reporting tools in serverless computing. So the providers or the major providers like Google, AWS, and Microsoft, they do not provide tools or metrics to let the users know what their carbon footprint is or what their energy consumption is. There have been some prototypes and approaches in the literature that try to estimate the energy consumption or the carbon footprint. FastMeta is an example. It enables lightweight function level energy estimation and reporting. GreenWhisk is a carbon-aware platform that is built upon the Apache OpenWhisk platform and which uses energy metrics internally. It doesn't expose them to guide, again, the internal load balancing to, at the end, reduce emissions. Now, moving to the users, to be honest, we haven't found many studies dealing with user-driven sustainability in serverless computing, but we could derive some approaches and some guidance, let's say. So when it comes to the user, it's all about making sustainable decisions. One of the decisions is choosing the region and the region of the deployment and the time of execution. So we know the user, whenever they deploy their function, they can choose the region. And there exist tools that can tell you how green some region is or some time of the day is, like the electricity map. So letting users have access to such tools to know what deployment region and time they can use can be beneficial. Even AWS present in their blog some guides on how to choose the region of the deployment in a sustainable way. Basically, what they do, they also tell the users to rely on the electricity map to have an impression on how green a region is. The other choice that can be made by the user is choosing the right server architecture. I mentioned it before, but there have been many studies in the serverless context about the implications of migrating serverless functions from x86 servers to ARM servers. And most studies show that the performance is similar to even better on ARM in some workloads, but the energy efficiency is much higher on ARM, and the cost is also reduced with ARM. It is worth noting here is that not all providers provide the ARM architecture as an option when it comes to deploying your serverless functions. Only AWS Lambda provides the option to run on either x86 or ARM. Now coming to the top and last layer, the application layer. And here it's all about the efficient code. So writing inefficient code leads to longer execution times, to more energy consumption. So optimizing the code of the user is a big step towards sustainable serverless computing. Now with the emergence of AI tools and LLMs, as I said, the optimization can be easier than before, but there are some considerations which I'm going to talk about, I promise, in just a moment. But beyond the algorithm, we have the programming language, which also has an impact on the efficiency and sustainability of the serverless workflow. Many studies have proven that different languages have different energy efficiency and execution times. One example here, maybe one extreme example in a specific workload, the Python code was 75 times slower than the C code and even the Java code, and also 75 times less energy efficient also than the other two. So the user can say, okay, I learned Python, I can only program Python. But again, the use of AI tools and LLMs can make the translation easier. And there have been several, or one framework in particular called ReFAS. It translates the serverless functions into more efficient ones by translating the code from one language to the other. Now we come to the consideration that needs to be made whenever using the AI, because as I said, we noticed a major trend of using AI tools and LLMs. Although LLMs can automate the code translation and make the optimization easier, the user needs to check whether the gains that come with this use justify the cost of the AI use, because AI agents or AI tools or LLMs, they come with their own sustainability issues, the big energy consumption, the big carbon footprints, etc. So the big consideration here is about finding whether the AI optimization makes sense or not. Now, to conclude our work, we can say that serverless computing delivers simplicity and elasticity, but its environmental impact remains insufficiently addressed, and we hope we helped fill this gap. So our systematic mapping study presents a structured taxonomy with the proposed solutions and the or with the challenges and the proposed solutions to them. Some insights is from our taxonomy is that there is still no standardized energy and carbon accounting monitoring systems included directly into the serverless platforms, which makes the evaluation of the sustainability of serverless platforms really hard. Most existing research focuses on provider-side optimization, especially scheduling, and neglect the user side. So optimizing the user code, the user deployment choices, etc. And the biggest trend, as I said in the recent papers, is the use of AI models and AI assistants to achieve sustainability goals. But the question that remains here, when do AI costs amortize against sustainability gains, as we formulated here? So we need to always consider whether the gains justify the cost of AI. And at the end, we can only say that sustainable serverless computing is a shared responsibility between the providers and the users. And all frameworks that were presented in our taxonomy need to be complementary. So this is an overview again of our taxonomy. with all layers. These are the sources that were referenced during the presentation. And thanks for your attention.
Yes, thank you. It was actually very interesting. I have maybe one very naive question. Is actually serverless computing really sustainable? Like, no matter what you do, you use resources, right? So in what sense is something sustainable? Only comparing between like one that is using less resources and another is using more, or is some other way to see?
In comparison to the traditional cloud, as I said?
Oh yeah, but like how? Yes, definitely. I mean, idle resources you want to minimize, but in general, like what is the ultimate goal for sustainable computing or sustainable serverless computing? Are we going to like put into space where it is really cold? And has no impact on Earth environment, would that be sustainable?
No,
Like optimal?
That's a very good question. I haven't included the definition of sustainability in the slides because we were constrained with the time. But we explained this in our paper. So achieving sustainability isn't just about decreasing the energy efficiency or decreasing the carbon footprint. So if you make the system use less energy, but you make it also 100 times slower, this is not sustainable. So achieving sustainability has to consider all sustainability aspects, which are performance, energy efficient, in the case of serverless at least, performance, latency, etc., and also the energy efficiency.
Right, but I understand, and I understand, that you can do payback. What do they call the carbon credits, right?
Yeah.
To make them neutral, but you're just moving cost from one side to another. Is that the goal? That like
How are we
build really big data centers and put a lot of trees in forests.
Yeah, I mean, what we show here is not, or we don't show that serverless computing is sustainable. Actually, the opposite. We show that there are many hidden challenges with serverless computing. This was the motivation or the first part of the presentation where we show that the people think that when using serverless, they are more sustainable, or because serverless promised a more efficient cloud, then we should just all use serverless. No, it depends, and there are novel challenges related to sustainability and related to serverless computing, such as the introduced cold start latency, for instance, and other virtualization overhead, etc. Because we run the functions in isolated environments, etc. So it's not about the fact that serverless is sustainable. It's about how we're going to make the serverless sustainable. Because as I said, it appears maybe more sustainable than traditional cloud, but if you dive deeper and look into how it works and the millions of instances that run, etc., then it's not really sustainable every time.
So one way to do it would be what you were saying. The biggest challenge is if all providers included not only the cost but actually environmental impact, like CO2 or whatever.
Yeah.
Not just energy usage, right? The kind of complete impact.
No, the sustainability. Yeah, I mean there's a framework which also is present in the paper. It's so sustainability consists of social sustainability, economic sustainability, and environmental sustainability. So to achieve sustainability, we need to address all three aspects. So cost, performance, and also energy use.
Yeah, hidden sometimes.
It's not always possible, but we try to achieve the best what can be done.
I don't know if there are any questions. Andy,
questions here.
Yes.
For the previous talk, do you have any questions?
No.
No. We're no questions here, Alec.
Okay, so we are concluding now. Thank you again, Andy and Kaiwen, for helping, to make that workshop happen